Hi, in this session we are going to study about the Gauss Law. Now Gauss Law is a fundamental law of physics and it kind of relates the electric field to the charge distribution that is causing that electric field. To understand Gauss Law properly, first of all we have to look at another concept known as the concept of electric flux. So this is what we will be discussing first, electric flux. To understand electric flux, what we will do is, we'll take a small plane surface in the form of a disk. So let's say our disk looks something like this. And for this disk, let's say we know the area of this disk is delta S. Then I can define another quantity for this disk known as the area vector. Now area vector being a vector, it will have two components if you want to specify it. First is its magnitude. The magnitude of area vector is given by delta S itself. Now we want to also know the direction. So the direction for area vector, just out of convention, is always given as the normal to this area, and there can be two normals, right? One could be this normal and the other could have been this particular normal. So we say, again out of convention only, we are not deriving it logically, it is something that we have fixed that we will follow this convention, and if we follow it systematically always, then the answers that I get or you get or some other scientists get, it will all be consistent. So that's the purpose of conventions. So according to this convention, what we are saying is, we will define this particular vector, let's say as a positive normal and the other as negative normal. Then this area vector has magnitude given by delta S and its direction is always the positive normal to that area. So this particular vector then represents our area vector delta S. Now let's move on to the concept of electric flux. Let's say that this plane disk surface area, it is exposed to some electric field such that the electric field line can be represented like this. Let's say this is our electric field and presently it's making an angle of theta with the area vector. Then for this surface, I can define this quantity called electric flux. I will denote electric flux, it's Flux, given by the formula phi. So this is the notation I will follow for denoting flux. So it's phi, and I can write phi is equal to the dot product of vector E and vector delta S, which is the area vector for this surface. So this becomes the expression for electric flux. And right now what we've done is, we have kind of derived it for a small plane surface which is in the form of a disk. Let's first of all play with this formula a bit so that we can know more things and know about it thoroughly. For example, what we can do is, if we expand this formula, it becomes equal to E delta S cos theta. So if we write this formula in this sense, let's observe what would have happened if the electric field was not making an angle of theta but was kind of parallel to the surface. Had it been parallel, let's say it was E1, then you see that the angle that this electric field makes with the area vector has become 90 degrees, and then if you plug in the values here, you will get E delta S cos 90, which would have become equal to 0. So whenever there is an electric field which is grazing the surface or is parallel to the surface, then the angle that it makes with the area vector becomes equal to 90 degree, and the formula you get, it reduces to 0 value. That becomes the value for flux. Also, if you notice that, let's say we've defined that this is the positive normal, and then the electric field is in this particular direction. Then if you find out E dot delta S, you will get a cos of 180 degrees, which is minus 1. So then the formula would have become minus E delta S. Only in one particular case, when the electric field is parallel to the area vector, you get this particular formula for flux as E delta S. Now before moving on further, this is one of the fundamental properties about electric field, its flux. So let's define its units. So the units of electric flux, you can see that here we have a Newton and here we have delta S. Delta S has the units for area and the units for electric field is newtons per coulomb. As such, the units for flux, if I want to write, it becomes equal to newtons per coulomb and then meter square. So this is the units of flux. We will be often using these units. Now let's kind of generalize this concept. First of all, what we've done is we've defined electric flux in a simplistic case where we have a plain disk surface. What if we have a surface which is irregular like this? And then if it is exposed to electric field like this, how do you calculate the electric flux passing through this surface? Well, the concept that comes to rescue here is the concept of calculus, which says divide and rule. You have to divide this surface into small surface areas, and we will take those surface areas so small that we will use this notation that we've been using called the differential area. So this time, let's say we have this small area, and here this small area can be represented by the area vector. Let's say this area vector is ds. And then at this particular point, let's say our electric field is like this, it's E. Then if you want to find the small flux that is passing through this particular area, you can write d phi, the small flux that is passing through that area, it's equal to vector E dot ds. Now, if you want to find out the total flux that is passing through this area, this irregular area, you can simply integrate this equation, and this is the expression you will get for flux passing through any irregular area. Now, when we will look at the Gauss law, we will see that it talks about electric flux for a particular geometry, which is that of an enclosed surface. It means that the area that we will be talking about, it will enclose a volume inside it. It may be a sphere, it may not be a sphere, it may even be a cuboid, it could be an irregular surface. But the condition that this particular surface should meet is that there should be some volume that is completely enclosed by it. So for this surface, also known as closed surface, my equation will look something like this. If I want to find out what is the electric flux that is passing through this surface, I will define positive normals. By conventions, for any closed surface, we take the normal that points outside as the positive normal. That is one of the conventions that we follow. And then the flux for the formula looks like this. It's just that what we do is we say that flux is equal to integration of E dot ds, and we put this sign to denote that if we are finding the total flux passing through this area is an enclosed surface. So this circle kind of denotes that we are enclosing this surface. So once we've got this idea about what a closed surface is and how can we define a quantity called electric flux for this closed surface, let's now move on to what the Gauss law says. To understand what the Gauss law says, let's take the example of this very same closed surface, and then let's say that we have these charges that are kept here. Let's say this is charge Q1, this is charge Q2, maybe this is charge minus Q3, and so on. There are a lot of charges here. So I will denote an nth charge Qn. And then I have some other charges also that are outside this surface. I will denote them with capital Q signs. So what I can say is there are external charges Q1, this is external charge Q2, and so on. So I'll say I have n number of external charges. Now, if I take any particular point and then find out a very small area within this point, it will be a small area vector. Then for this particular area vector, I can define this quantity called the differential flux, which will be the electric field due to all these charges times this area, right? And then we will do the dot product there. So that will be the electric flux due to this small area, or passing through this small area due to these charges. Then the statement of Gauss law says that the total flux that is passing through this area, which will be denoted by this formula, mind you, if we can find E at different points, it will be different for different points, right? So this E will be a function of some other thing, it will be a variable. Then E dot ds, this particular thing, is given as Q enclosed upon epsilon naught. So this is the statement of Gauss law really. I'll write Gauss law here. And then let's try to look at what it really means. So it says that if you want to find out the electric flux over this entire surface, what you have to do is, you have to, in the right hand side, we have Q enclosed, only the charges that are enclosed by the surface. So what qualifies? Q1 does, Q2 does, minus Q3 does, and so does Qn. But do these charges qualify to come here in the right hand side? Capital Q1 is outside, right? So it doesn't. And same for all these other charges. So the statement of Gauss law says that although the electric field at any particular point will be due to even external charges, but if you find the sum of the electric flux for all these small areas, that will be the total electric flux that is passing through a closed surface, then that electric flux can only be calculated if we know what are the charges that are enclosed by the surface. So this is a very important result. It's treated as one of the fundamental laws of physics. And the statement is this. It says the total flux passing through an enclosed surface is given as Q enclosed upon epsilon naught. And if you wanted to find out Qn, in this particular situation, what would you have written? It would have been summation of Qi's, where Qi's are the individual charges that are inside. We wouldn't have concerned ourselves with capital Q charges, right? So our formula would have become something like this for the Gauss law. Now, this being a fundamental law, we don't even need to prove it. A fundamental law is something that is only validated by experiments always. It has never been violated. And we don't need to prove it by logic or derived it. However, it so happens that when the Gauss law was discovered, Coulomb's law had already been discovered before it, and people found out that it is possible to start from the statement of Coulomb's law and get to Gauss law, so through a logical series of steps. So although we don't need to derive this particular law because it's a fundamental law, I think it will be a fun exercise to see how we can start from Coulomb's law and then through a logical chain of reasoning arrive at this particular equation. So this is what we're going to do now. Now, if we have to start from the Coulomb's law and get to Gauss law, we have to first of all understand the concept of a solid angle. Now you might have learned about the plane angle and must be wondering right now what a solid angle is. So because a solid angle is a generalization of plane angle in 3 dimensions, what we will do is we will take the help of analogy with the plane angle and understand things about the solid angle. So what we can start with is, let's say we have this line segment here. Let's call this line segment AB. Then for any point O, we can say that the angle that OB and OA make with each other is theta. So we can say this particular situation or describe this situation like saying, if we start from point A and move to point B, this particular thing, this line segment will subtend an angle at O, and that angle is called the plane angle theta. Similarly, what we can do is, we can define a solid angle. If we consider here, what we are doing is, we are starting from one of the endpoints and going to the other endpoint, and in doing so, we see that if we join all the endpoints, it subtends an angle at some point O. This is called a plane angle. Similarly, let's see how a solid angle can look like. In a solid angle, instead of a line segment, what we have is, we have a surface. Let's say this is our surface, and if for this surface we consider all the points that are in the periphery of this surface and join them, and then let's take a general point O, then what we can see is, if we project this particular thing here, you can see that at this point O, there is a three-dimensional angle-like thing that is being subtended. So this is the exact meaning of a solid angle. Now, this is for a qualitative sense, as in now we can know what a solid angle is if we know what a plane angle is. Let's try to quantify this quantity called the solid angle. To do that, we will again follow this analogy. We will first of all see how we quantify a plane angle, and then we will see how we can quantify a solid angle. To do this, in case of a plane angle, we can see that theta, if we take this line segment or this curve rather, AB, this time let's take it as a part of the circle, meaning it is an arc right now, and let's say the length of the arc is L, then this angle theta becomes equal to L upon R, where R is the distance of that point from these points in the periphery. And now this is how we can quantify a plane angle, right? So similarly, we can quantify a solid angle. In solid angle, we will take this surface as part of a sphere, and then this, if you take all the points in the periphery of this particular part of the sphere, you can see that they are subtending an angle theta at the center, or O, let's call this point as O, and let's say all the points are equidistant from this peripheral points. Then what we get is, let's call this distance as R. Then solid angles formula, we can denote it with the symbol omega. It becomes equal to delta S upon R square, where delta S is the area of this particular surface. So let's write this here. Theta, which is the plane angle, it is given as delta L upon R. Similarly, if we call this as R and this as delta L, similarly, solid angle omega can be given as delta S upon R square. So this is how we quantify solid angle. This is its expression. Just one more modification to this equation. Let's say in this particular line segment, this line is making an angle of alpha with the normal to this line and point O. In that case, if you want to write theta, then theta, you can see this, if you project a normal line to this particular thing, we get a delta L cos alpha this time. So the expression for theta becomes delta L cos alpha upon R. Same kind of logic can be applied in case of solid angle. Now we have totally generalized it. Here you can see that there is an angle that is making an angle of alpha with the normal to the surface. Then if we want to generalize the solid angles formula here, we can say that omega is equal to delta S cos alpha upon R square. So now we can define angles, plane angles as well as solid angles for all these cases and a general case as well. So after making this generalization, my formula modifies to cos alpha here and cos alpha here. So in a sense, we have learned now how to calculate the expression for solid angle subtended by a part of a surface, a very small surface. The next thing that we are going to learn and consider is what is the solid angle subtended by an enclosed surface which encloses certain volume inside it. To do that, we will again take help of the concept of the plane angle. In case of a plane angle, you see, if we decide that if we have to find out a total angle subtended, let's start from one of the points. Let's say this point is A, and then we will fix the sense of rotation. Here we saw that the sense was kind of anti-clockwise. Same sense will follow here. So in that sense, if we move from this point A to a point which is in the opposite direction, let's call this point A dash. You can see if A and A dash are very far away from each other, then they subtend this angle. However, if points A and A dash are brought close to each other, you can see they start subtending an angle of 2 pi here. How do we get this 2 pi? If we apply the formula delta L upon R, here the length that is subtending this angle is becoming equal to 2 pi R, and then if you divide it by R, you get the total angle enclosed as 2 pi. Let's do a similar kind of thing for a solid angle. Here we have an enclosed surface. Let's take a point inside it. For this point, let's try to find out what is the area that is subtending an angle. It's this particular one. And then if you want to find out the total angle being subtended by all the points here, just like we had calculated the formula there as 2 pi R upon R, here we have delta S. Delta S becomes equal to 4 pi R square if we sum it up, and then we divide it by R square, and we get the expression for total angle subtended. It becomes equal to 4 pi. Right now we've taken very symmetric geometries. We've taken a circle here for a plane angle and a sphere here for a solid angle. However, now let's modify these geometries. Let's take general geometries. This time instead of a circle we have some closed loop there, and this point is not even in the center, it's some other point. Let's visualize how we can say that the total angle subtended is the sum of angles subtended by individual small segments there. It looks like 2 pi, right? Similarly, if we consider this particular case, in case of a solid angle, if we take a general surface and a general point, you can see the angle again becomes equal to 4 pi. Finally, I want you to consider this one modification to the situation. Instead of taking a point inside the loop or the surface, let's take a point outside. And then, let's say if you want to find out the total angle subtended, then we'll take 2 points that are very close to each other, and the approximate value of the angle they subtend can be kind of extrapolated, and we can find out the value subtended by the total points. So here, if you see that if the point is external, in case of a planar geometry, the plane angle becomes equal to 0, right? Similarly, in case of a solid geometry, the angle that we get is also 0. So this is one important conclusion. I would like to summarize it here. What I mean to say is, in case of a plane angle, if we have a closed loop, the total angle subtended but at a point inside is 2 pi. So I can write 2 pi here for inside, and for any general point that is taken outside this loop, the angle subtended is 0. So this is for a point outside. Same way, we can say things about the solid angle. So in place of a closed loop, this time we will have a closed surface. And if we take a point inside, then the total angle subtended there is 4 pi. This is for a point inside. And if we take a point outside, then the total angle becomes equal to 0 radians. So once we've made these generalizations, we've looked at the concept of solid angle. Now we're good to go. Let's see how to start from Coulomb's law and get to the Gauss law. So for that, what we will do is, we will consider a general closed surface, and then let's take only 2 points right now. Let's say this is point charge Q1, and then we have a point charge capital Q1. Small q1 is inside the surface and capital Q1 is outside the surface. Now, let's take any particular point here in this surface, and around this surface, let's consider a differential area ds. So right now, we will not consider this point, we will consider it later. Let's say there is only this charge Q1, then let's say it will have some electric field. The direction of electric field is something like this. It is E, and if we say that this is R, the separation between this particular point A and this point O, then OA is R. If we want to write out the expression for electric field, let's write only the magnitude right now. Then E becomes equal to K Q1 upon R square. Now what will be the flux here? If we want to find out the differential flux passing through this small area, it becomes equal to E dot ds or E ds cos alpha. And if we substitute the value of E here, our expression becomes d phi equals K Q upon R square, and then I have a ds cos alpha. Now, let's consider this ds cos alpha upon R square. We've seen here, it looks exactly the same form, right? So what we have here is KQ times the solid angle being subtended at this point O by the small area around A. So I can write this equation this time as d phi, and now I'll even expand the value of K. I'll write it as 1 upon 4 pi epsilon naught. And then I have a Q1, this is Q1, times d omega. And now, if I want to find out the total electric flux, what I can do is integrate this equation here. So 1 upon 4 pi epsilon naught and Q1, they're all constants, so they'll come out of the integration sign. And I just have to integrate this expression for d omega. This integration will be equal to omega. So what I have here is, this is flux, and here I have Q1 upon 4 pi epsilon naught, and then here I have omega, and this is total omega due to this enclosed surface at a point inside the surface. So I think I should use this particular expression. I've already seen it, right? We've looked at it together. So this quantity here, this integration, becomes equal to 4 pi. And then it becomes a piece of cake to cancel 4 pi's from numerator and denominator. And we get the flux due to this particular charge. We will use a specific notation for it. Let's start using the subscript phi 1 here and in these places also. So this is the general formula. And from here, we have found out that the flux due to this charge which is inside the surface is Q1 upon epsilon naught. Now what is the flux due to this particular point, capital Q1? This point is outside the surface. Let's see where this particular expression changes due to the fact that this point is outside the surface. Till here, we can write the same equation. Instead of small q1, we just have to replace it with capital Q1. And even till here, the only difference that comes is this time we have to integrate the solid angle due to a point that is outside, or at a point that is outside the surface. And for that, this integration doesn't become 4 pi, but it becomes 0. So if we denote this particular integral as phi 1 1, then I get Q1 upon 4 pi epsilon naught times this integration is 0. So I get a 0 here. Now, I've looked at these two particular cases. If a point is inside, the flux due to this particular charge is Q1 upon epsilon naught. If a charge is outside, then the flux due to it, overall flux through this area, it is equal to 0. Let's generalize this. What I'll do is, I'll make a different diagram this time. And this time I have a lot of charges here, Q1, Q2, and say till Qn. And there are external charges also. I'll denote them by capital Q. So I have a capital Q1, capital Q2, and let's say a capital Qn. Then, if I want to find out the total flux that is passing through this area due to all these charges, I'll take one point here. Let's say this point is A, and let's take a small area around it. It will be called ds. I can draw it like this. Now, if I want to find out the differential flux, what I can say is, first of all, let's find out the electric field at this point. We will use the principle of superposition. It says that the total electric field at this particular point is equal to the electric field due to this point Q1, due to this charge Q2, and then we will add up all these electric fields. So I can say E is equal to E1 plus E2 till En, and then let's say due to charges that are outside, the electric flux or electric fields are denoted by the subscript 1, 1, and here I have 2, 2, and so on till En. Now, if I found out E, then it's easy to find out the total flux that is passing here, which is E dot ds. And if I want to find out total flux, I just have to integrate this equation. So over the closed loop, what I will get here is, this is flux here, and here I have integration of E1 dot ds. I'll write vector signs here, and so on, right? So I have these integrations till this particular point, En dot ds. Now, for a point that is inside the surface, this quantity E dot ds, it's simplified to Q1 upon epsilon naught. And for a point that was outside, for example, En, this quantity became equal to 0. Let's use these results. We can express phi as Q1 upon epsilon naught plus Q2 upon epsilon naught, and so on. And then these are for internal points. For all the external points, I will have to write zeros. So if you sum it all up, or kind of summarize this result, what you get is phi is equal to summation of Qi upon epsilon naught, where Qi are the internal charges. Another way of writing it is phi is equal to Qin, or enclosed charge, upon epsilon naught. There. We started from the Coulomb's law. It said that K Q1 Q2 upon R square would have been the force, and consequently the electric field would be K Q1 upon R square, and we reached at the Gauss law. This was as a result of Coulomb's law. And this is the statement of Gauss law. Now we will see more applications about the Gauss law, but all of that in the next session.